Assalamualaikum warahmatullahi wabarakatuh and hello, salam sejahtera. So today we are going to learn about modified Newton-Raphson method for finding roots of equation. As we already know, we are still in chapter 2, which we learn about numerical methods on finding roots of equation. So what we have learned so far, let us see. So just what we have learned a few weeks ago, which is open methods. The first one was one-point iteration method. So from one-point iteration method, we understood that it is very good to be used for function that is expressed in the form of implicit expression. It is very simple, and we know that it might have some kind of possibility of divergence, which means it does not converge during the iteration in order to get the approximation. So when it diverges, meaning that the approximate error becomes larger, so we cannot get the good approximation. Okay, and then we have learned as well Newton-Raphson method. It is one of the most used method to solve roots of equation. The reason why it is most used because it is effective and can give fast convergence in order to get the roots that we are looking for. However, this Newton-Raphson method, if you look at the formula, it shows that you need to calculate the first derivative, which means the gradient of the function at that particular point. So let's say if you have a function which is very difficult to find its first derivative, very difficult to differentiate, or maybe even impossible to get the first derivative out of the function. So meaning you cannot use Newton-Raphson method. So if that kind of problem occurs, you can use this alternative method, which we call as secant method. Okay. Compared to the one-point iteration and Newton-Raphson method, this secant method requires you to have two initial guesses. So the previous two methods only require to have one initial guess, but for secant method, it requires you to determine two initial guesses. So meaning you need to have more information in order to apply this method. One of the advantage of this secant method compared to the Newton-Raphson method is that you don't have to calculate or to express the first derivative of the function that we are dealing with. Okay. Alright, so we have three methods that we have learned previously under the category of open methods. Okay. Now we talk about multiple roots. What is actually multiple roots? A multiple root is a root with a multiplicity of at least 2. So 2 or more. It can be 3, 4, and so forth. So when you have a root like that, you call it as multiple root. For example, in this equation, x minus 1 in bracket square equal to 0. So the root is 1, and the root is not a single or simple root, it is a multiple root, in which if you take a look at the equation, you can expand it in this form: x minus 1 equal to 0. So how many roots you have? You have two roots, which is x equal to 1, and the other one is x equal to 1. So this kind of root, we call it as multiple roots. And if you can see in the figure above, where the root occurs, you can see that the curve touch the x-axis tangentially. It means that it goes down. In this particular graph, it goes down the curve from left to right, and then it touches the x-axis. And at the x-axis, the curve is tangential to the x-axis, and then it goes up back. Okay. So there are other example of multiple root, double root. So the previous example was a double root as well. So this is another example of double root. The function says it is a cubic function, but if you expand it, it will look like that: x minus 3 times x minus 1 times x minus 1. So you have 3 roots because it is a cubic function, but 2 of the roots are actually the same root, the same value. So you have x equal to 3 as the simple root of that function, and you has a double root at x equal to 1. There's another example of multiple root, which is triple root. Okay, this time it is a function to the power of 4. Okay, so you can factorize the function x minus 3 times x minus 1 to the power of 3. So you have a triple root at x equal to 1 and a simple root at x equal to 3. So in this example, it is a function up to the power of 4, meaning you need to have 4 roots in order to define all the roots that it has. So you have 4 roots, you have 1 simple root, so meaning 3 roots left, and in this case you have triple root at x equal to 1. So the total number of roots are 4. By looking at the figure, okay, you can see figure A, it is a double root, and then figure B, double root as well. Okay, figure C, triple root, and figure 4, quadruple root. So you can notice that in general, a function with odd multiple roots, for example in figure C, okay, the curve crosses the x-axis. Okay, so you can have the curve going down to the x-axis and then has a tangential condition between the x-axis and the curve, and then it goes down under the x-axis. So you can say that for the odd multiple roots, the curve crosses the x-axis. Whereas a function with even multiple roots, like in figure A, B, and D, okay, the curve does not cross the x-axis. The other thing that you can observe in this figure is that the first derivative of the curve at the multiple root is 0, or in other words, the gradient of the function or at the particular multiple root is equal to 0. Okay, so why we talk about this? Because we will use this behavior or observation in order to lay out the method in order to solve multiple roots. So when we talk about solving roots, consequently, multiple roots pose several limitations for the numerical method discussed earlier, such as the Newton-Raphson method, secant method, or maybe other method that we learn in bracketing method, which is bisection method, and the force position method. So these 3 methods is actually has some limitation in order to solve multiple roots. Why? Because most of these methods, the previous method I mentioned just now, can solve one root at single time, and it cannot determine whether the particular root that it has solved is multiple root or a simple root. So for a function with even multiple roots, the function does not change sign over the interval. Thus, it eliminates the use of the reliable bracketing methods. And the other thing is that at the multiple roots, both the value of the function and the derivative of the function at the x-axis are 0 or approaching 0. So this poses problems when we try to use Newton-Raphson method or secant method in order to solve the root. For example, in Newton-Raphson method, if you take a look at the formula, Newton-Raphson method formula, you will see that you require to put the first derivative at the denominator. So if understanding that the gradient of the function for the multiple root is 0, so you need to put 0 at the denominator, meaning you cannot solve your multiple root using Newton-Raphson method because you have to divide by 0. So you need to find another way. So to overcome these two problems, we will use a modified Newton-Raphson method in order to solve multiple roots. So let us introduce the new function as gx. Okay, so gx is actually the ratio of the function and its derivative. So gx is equal to fx divided by f prime x. And then we differentiate the function gx using quotient rule. So we will have the one in equation 2. And then we apply Newton-Raphson method, the original Newton-Raphson method, to the function gx and the derivative g prime x. So we will have xi plus 1 equal to xi minus gx divided by the g prime x, as shown in equation 3. And then what we do is we substitute equation 1 and 2, the gx and g prime x, into the Newton-Raphson method as in equation 3. So we will get this equation 4, which is xi plus 1 equal to xi minus, in the numerator, the function xi multiplied by the first derivative of f at point xi, divide by the square of the first derivative of fx, minus the function f multiplied by the second derivatives of f at point xi. So you can see that it looks similar to the Newton-Raphson method, but it has been modified by applying the new ratio of gx. So take note that in the denominator, okay, even though if the first derivative or the gradient is 0, there is no problem to solve this formula. Unlike the original Newton-Raphson method where you have to divide by the first derivatives of f. So if you have the first derivatives equal to 0, so you cannot solve using the original Newton-Raphson method. That problem will not appear in this modified Newton-Raphson formula. Some remark the convergence for the modified Newton-Raphson method is quadratic or second order. Unless necessary, this method is seldom used in practice due to more computational effort involved.